Okay. Which one, since that we'll chat about homeworks, theoretical homeworks. So which one of them? All? To start with, prioritized?
All is fine.
I can tell you which ones are easy. Number 3 is easy.
Okay.
That's pretty straightforward. You showed us how to do it in class.
I raised my hand and got incorrect.
And I knew how to do it, but I didn't raise my hand.
Oh, I feel like
Okay.
Could we maybe start with number 2?
Yeah, we definitely since most of the day today will be on number 2, that we can definitely, then let's wait with number 2, because that's exactly, it is which has the easy part and the tricky part. Exactly how we are using 2 passes for the windows. Here I just wanted to know that you can squeeze from the coordinates of a billboard. You know how to transform the billboard so its origin is on the XYZ. The origin is at the origin of the billboard, lower left, say, of the billboard. You notice that, not that usually I'm very clear, but today and last meeting I was like bad. Yeah, we have a billboard, probably in a different color for the sake of the camera. Lower left, upper left, lower right, upper right. Transform it, give a transformation, translation that brings the lower left into 0, 0, 0. Help? I mean, that's where I should definitely start. I mean, I also want to rotate it so it's oriented to, say, to the X and Y axis. But to start with, here is my billboard. Here is my billboard. Pretend that it's a rectangle. It's oriented in some strange angle, and I want to bring it, to find the translation, that bring it so its lower left corner coincide with 0, 0, 0. Should be automatic to all of you. Help? What is a translation?
Translate by negative.
Translate by minus lower left. Now we need to rotate the whole thing after the translation, and the order definitely matters. So how can I find rotation matrix? Can do it in the quick way or the long way, and I wanted you to use the trick, it's usual. We want to use in the whole course. I'll mention before that if I tell you that the billboard is already in the XY plane, but say it's the whole billboard is in the XY plane, but it's rotated in the wrong angle, then you can compute this angle and now rotate by theta. That's theta, rotate by theta around which axis?
The origin.
Sorry?
The origin.
rotate around, yes, but we had three matrices that we showed in 3D. It's all live in 3D except that it's, yes, it's rotated around the origin, but usually when we talked about rotation in 3D, it's rotation around one of the axes, for example. Or I'll give you a vector u and I want to rotate around the lines that you defined. So which axis do I rotate it around?
The z-axis.
The z-axis, the one that goes only. That's exactly like rotate. But rotate around the x will take it over here, and rotate around the y is this operation. Okay, but if it's, but I don't want you to do it in a multi-step process, rotate around the x, rotate around y. Instead, what I want you to do is help.
Could we maybe use dot product to the x-axis? Or comparing, actually, no, never mind, ignore me. I was gonna say taking
No.
the vector from lower left to lower right and then dot product to get cosine of that.
That works when it could work. It's not the quickest, but it can work if it is indeed in the XY plane already and it's all in 2D. But the billboard is oriented somehow in 3D. Any global orientation. And it's a very legit question for the test because I highlighted this point multiple times. So, you know, it's not what important for the course, it's what I feel insulted when you are, yeah, it's, I think, I'm not saying it seriously, trying. Okay.
Are you talking about building a translation matrix?
Building a rotation matrix, and the step to build a rotation matrix is to, I think that you have the right meaning, but I mean, if you didn't do it, then I assume that then I have suspicious about what you did in homework too, even. Spit it out.
Combine the matrices for
We start by translation. So assume that its lower left is already at 0, 0, 0. But its lower left, maybe I need to take something that is a bit more similar to billboard. Its lower left is already in the origin, 0, 0, 0, but it's oriented completely in the wrong way. I need one matrix that will orient it so it's in the XY. I mentioned two basic ways to build a rotation matrix. One way was to decide by how many angles I need to rotate it. That's a long and not very convenient way. It's not that we don't need it at all, but we use it when we talk about animation. If you have a body that is rotated, even if for homework 2 you have. If you have the starting position of the camera with the look at, and the ending position, I think at the time we didn't have change of angle, but if you have a change of angle and you want to create an animation, then usually for small enough angle, you can rotate, define by how much I should rotate by X, by Y, and by Z, and combine the three rotations. It sometimes can work, especially if the whole animation is for small enough angle. But it would be really not convenient in this case.
We would want to use quaternion rotation.
Oh yeah, that's in animation. That's all coming up. Not here. Here my problem is very simple. I want to rotate the billboard so only its vertices are on the XYZ, on the XY plane. he intercepts it. So here's a u vector, here is a v vector. You needed to build the u and v for each billboard for homework 2 to find the coordinates of where it meets. So let's compute u, which is as usual lower right minus lower left, normalized by the length of lower right minus lower left. Unit vector that goes in the u direction. V, which is similar, which is analogous, right? The upper, what is the upper left minus lower left, normalized. And I also need W, because I'm going to build a coordinate system that's a billboard by itself defined. So W help
Cross products.
the cross product, and if I want W to face toward you, then the W needs to go to this way, right? So it would be U cross V. And now, same question, what is rotation matrix? Put U, V, and W. Just, what do we mean U? It's, I can think about it as an abstract vector, or I can really think about its representation in the XYZ coordinate system in the Euclidean world. These are the three numbers that it represents, the three numbers of V, the three numbers of W. Write these 9 numbers as so. You could make it, of course, add 1 here to make it, a homogeneous coordinate. And I argue that this is a matrix R that I need for the rotation. Why? Because what happened to the vertex, to the vector U, I wasn't very careful about left hand, right hand, but I want the vector U after the right rotation to be aligned with the x-axis. So U dot product. That's what you wanted to. So it's U, V, and W, because it takes this matrix. Where does it take the vector U? It takes the vector U, but R dot U is 1, 0, 0, which is just the x vector. And same for, it will take V, and align it with the W. And if these are where these two vectors are, then actually I don't care about W's, and obviously if these two vectors are in the XY plane, these 3 points are in the XY plane, that's the whole billboard is. So if you want to practice more of this, then how do I rotate, sorry for the recording, how do I rotate by theta? It's already a preparation for the midterm. Rotate by theta around the vector, around A given vector, which vector do we see? C mu. Mu is some vector that I gave you, say a line that goes through the origin, so mu, and I want to rotate the wall when my camera points at this direction mu. And I want to rotate it by 5 degrees. How can I do it? Well, if I already built for the user coordinate system, that's what I suggest. Again, we are wasting a lot of time by defining the matrix, but now the matrix is used for every point in the plane, and that's what every time that our GPU looks at a point, it first multiplies this point by the matrix that we are building. So I want to rotate by theta degrees around the vector W. I need to tell you clockwise or around mu over there. It's a different question. There are no billboards, but it uses the same idea. that is rotate by theta around the line 0, 0, 0 plus t times mu. Example, mu equal 1, 1, 1, x, y, z, then I'm rotating around this line. If mu equals 1 by 1, 1, 1, and I want to show you the world right after this rotation. How can you do it? Well, you'll pick W, say, that goes along this direction. Call this direction W. W is just mu. Highlight between mu and mu. And now pick I'm going again to build a coordinate system. So I have the first vector, that is u. I have now I build another vector, any vector, I don't care. I have a whole plane of direction, a whole circle of direction to pick from, but u needs to be orthogonal to w. And now you have W and you have U, and pick V. U cross a W. And you have your coordinate system, 3 vectors. It might be minus here. That's, I need to double check. It might be that I need minus here. Okay. Otherwise, I need to rotate by theta counterclockwise instead of clockwise. Again, first vector is given to you. Second vector, I don't care, just orthogonal to the first one. And third, and now when I have these two, I'll generate a third one by just a cross product. And now what is my rotation matrix altogether? I'll say that the matrix that I need, the rotation by theta around a mu is what? I'll take every point P, I multiply P by the rotation R. So now P moved, so if P happens to be the U mu vector, it will go into the x vector. We'll double check it in a second. So again, I'm jumping a bit. R equal once again U as a row, V as a row, and W as a row. What happened with this vector? Once again, with this rotation matrix, sanity check, R times mu, R times W is the, help? Well, I changed later at the end, so that R times mu will be 1, 0, 0, meaning the x vector. And obviously for x, obviously for y. And now, what is my rotation matrix altogether? Start by taking a point P multiplied by R. Now the whole world is aligned with the x, y, z. Now rotate R theta, where R theta is rotate around, since I align mu with the x coordinate, then it's rotated around the x. It's just the same matrix that we had before, just slightly around, yeah.
Shouldn't it be Z because W is mu?
In this case, see, I could, oh yeah, W equal Z, so yeah. So R of mu equals the Z vector. So I rotate by theta. R theta is rotating around the, now it's rotating around the Z axis. So I'm almost done. And now I need to, after rotation, I need to put everything again so mu points to the mu direction. So times R minus 1. So the product of these three matrices is the matrix that I need. Everybody sees? Everybody understands? I'll take you right. Yeah.
And then how do we calculate the inverse of that R matrix? Is it just the transposition?
Excellent. So if R is U, V, and W, then I can use, there are 9 numbers. I can use diagonalization, for example, that's a long and unnecessary way to compute what is the inverse. Remember, UVW are unit vector all the time. But what's true about any rotation matrix, it takes a proof why it's true for any rotation matrix. But for any rotation matrix, R minus 1 is nothing but take U as now a column, V as a column, and W as a column. Copy it again because it's so this whiteboard. So if this is R, what does this matrix does for us? U, V, W. That is what we call R. And now let's take U, V, W, but now with 3 columns. That is the transpose of the matrix. What is the result? U times U times U, 1. V times V, 1. W times W, 1. U and V are orthogonal to each other. So U times V, 0, 0. So what did we study? That this matrix is the inverse. That I thought pretty cool. You don't, the moment that you have your coordinate system, for the billboard it was quite easy. Here is a smooth way to move from one port to another. Okay. So this was about rotational matrices. And you need it when you're building the matrix. Doing homework 4 and from the future, I want you to understand the whole viewing process of taking the world and perspective transformation and squeeze it and do the viewing wrapping, the viewing distortion projection until it fits into the canonical volume, which was involved from first. It started by, let's take the camera and the view direction and the up and just translate and rotate, still not scale, just translation and rotation, so the camera moves into 0, 0, 0. Why again? Because your GPU wants it to be at 0, 0, 0. Except that you don't really apply it. You don't change your data itself. You just say, hey, vertex shader. The moment you're looking at a point pi, what you really see is the matrix M times pi. and do it for each point. Matrix n times, yeah, you're not changing the data, you're just passing it and as, how did we call this type of data? Another midterm question. How do we call something that the CPU sends into the GPU, into the shaders? Uniform. What we're varying with uniform. Uniform meaning it's the same and no change. It's not individual per process, not individual per shader. It's the same matrix as common attributes that all shaders, fragment shaders, pixel shaders, vertex shaders, all know about, but they cannot change it. Only your main program on your on the CPU itself can change it. Okay, so that was about rotation. Help? Here is G, that was easy. 6, here is G. What is G to the power 72? G times D, G times G, 72 times.
It's just rotate by 5 degrees.
Rotate by 5 degrees, and then rotate again, and then rotate again. Each time you're rotating by 5 times 72, whatever this number is. That's the result of this. Again, would be ugly to find without realizing that it's a rotation matrix. Okay, and the same goes a few times in different homeworks as well. How did you like this question?
It was interactive.
So will you see, like I have a viewer somewhere, viewer that, or I'm creating an image from the viewer that is right here. And in the image you see this ball, the red ball and the blue ball. Will the red appeared in the image from the viewer point of view? Will the red appear to the left or to the right of the blue? It's a great exam question, especially if I don't give you access to it, because I know who actually played the app and who not.
Is it to left? Is it to left? The red would be the left and blue.
And
Right back.
the answer is that it depends. Right? Think about, there is a focal. If the eye is right here, then red is to the left, then red is to the left of the blue. Now, as I change my direction, there is some focal point where if all of them meet, and then if I'll continue, then on the left side I see the blue ball, and on the right side of the camera I see the red ball. So that's a point that the whole world collapse and switch it over. Think about what is the image that you see as you're walking across this corridor toward this direction. Let's do the math. How do I compute the vector v? it's something that I think that it's pretty good exam midterm question because it gives me hints about what you did in the different homeworks independent. So here is a semicircle. Radius is R, let's call it 0, 0. And here is a point P on the semicircle, and I define N to be the normal at P. And my question for you is, given P as a point, how do I compute N?
Just we do P minus origin, nominal.
P minus the origin, almost. P minus the origin is what you'll use in the homework 2-3 when you had spheres and you needed the normal of the spheres for the shading. But that's the normal that goes outward. So it's minus. It's the other one that goes toward the center. Okay, from this point, again, good check for the homework. How do I know what is the direction reflect from the camera to the viewer? I have, here is the eye, here is the point P, for each point P on the sphere. Let's say you're doing ray tracing, here's the point P. I want to compute what is the direction of R. We explained this direction. It is the direction of R, I don't normalize it here, but the direction of R is L minus 2 times N dot product L dot, now N times L is a scalar, times N once again. What was the intuition? I need to clean it a bit to make sense. Now, all these questions, let me to ask me about the midterm, all these questions is something that I think that are some fundamentals that you need to know, but it's by no means, it's a necessary part, but it's not the cool part, nor the important part of the course. Right. Important, yes, but right. I'm not going to bombard you in the whole midterm about if I don't find something cool, which is completely subjective, then I would like to minimize how much it appears in the midterm.
Should we get a list of everything you think is cool?
I need to show by examples. So, but as an example, the idea of using the matrix by generating coordinate system and using it as rotation, I think that it's much cooler than what textbook will suggest as the first step of first compute the projection on the x direction, y direction, compute well, this rotation times this rotation times this rotation, and so on. So that's between the two of them. But we had plenty of cool ideas out there, right? At least. And again, what was the intuition behind this direction? You have a vector L hitting the point at the point P. L has x coordinate and y coordinate hitting the point P. What is the direction of the total reflection? Direction of R. R is, if I know what is the x and y, x, y, z in three dimension. If I know what is x, y, which I can always do by isolating from the vector individual parts. I just prefer to have this equation because dot product, as we mentioned many times, our GPU likes it. But R in this case is, we talked about it. We have a fly or a basketball that moves at velocity v, bounce, and continue in the same velocity, mysteriously doesn't lose any energy, moves in the same horizontal speed, but its vertical speed is just reversed. So R is just x and minus y. And if you think about this, what this formula is doing, then L times n, L times n is nothing but y, this value. So I'm just taking R and adding to it 2y in this direction. Other things from the homework? But same idea, except there's parabola direction. Then there is direction. There is a focal point. You know that when you are there, the same way that how you build antennas. When all your rays come from infinity, they'll all concentrate into this eye. If you are just at the focal point, that's where the difference between them. Okay. Yeah, going through all the, you can use this part, or you can solve it by, let's just consider the x and y, use what you hopefully know from if you don't like partial derivative, you can just leave by x and y, and now assumes radial symmetry. Just for every point, I'll just rotate it by the right amount, and all the normals around the concentric sphere. If here is my antenna, and this is a circle of direction r, then all the normals here goes, well, it's not exactly the same direction, but if I'll pick one r, sorry, if it bounces in direction r over here, then rotate it around you, and you'll get the normals, the rotation direction from any other point. It's just like 1D, except exactly what you expect. This is 2D problem that is function of x and y only. And for every such point, you want to know if you're at a different direction, rotate everything by theta. Hopefully this hand wave made any sense. Other questions from the homework? Nobody said anything. Should I understand it as? Like, that's will be useful in homework 5 or 6 if we'll do the pools. We didn't decide yet. But if in the pool exercise we dropped a pebble, a stone, into a water, and the water creates ripples on the water, but you have circular symmetry around the points where the pebble hits the water, so all the other pebbles go around you. You need the normals because you have reflection and refraction, but you can solve it as a 2D problem and just take your solution and rotate it for every by theta. Much easier to think about it in polar coordinates. Nobody? Yeah.
So now when you ask us what coordinate systems have we discussed in class, do we need to add polar to that list?
No.
Okay.
No, and I don't. I'm trying not to be nasty. I'm trying not to say, hey, you are way better than me in graphics. You have 10,000 lines of code, but you missed a class, and that's why I'll really get revenge. I'm trying not to be this person. I'll be back in a second. Something big.
Yeah, I did 1, 2, 3, 6, and 7 so far. I haven't done any of the GeoG problems.
I finished for this class.
But going through the number 2 is really helpful. So I guess that's why it's upside down.
That's not necessary.
How did you get the connection? How did you get the connection?
I mean, like purple, I could do all the other ones, but that's the purple. I can't do that purple at the end.
Wait, how'd you get fucking extensions? Like that was, I feel like that was something.
I do a lot of connection. I'm good at
That was,
those.
you're just at there.
What?
At there.
Yeah, yeah. That's why I smoked you in that little LinkedIn one.
Keep doing that.
Anything else from the homework? You almost said something. Spit it out.
That's okay, that's okay. I'm pretty sure I got it.
I would ask you.
So.
Oh, really?
I mean, it's a discussion,
Tell me
it's
the
a
question,
group.
I'll ask the question.
Question have more than one solution. There is no ego involved. I'll criticize you for not participating. I'm not criticizing you for giving the wrong answers. I can go on and on. Yeah.
I'll ask this question. Is question 10 graded for undergrads? If so, it's not like selectable on CreateScope. That's it. Did anyone else have a question?
Okay, so, I mean, if you don't select it, it's fine. I can find your answer.
I just included it with number 9, but like, there's no option to select number 10 and like select pages.
Okay, maybe I made a mistake. So.
I didn't extend it. By the way, how many of you took some calculus? Know that it's, yeah, it's in there. Great.
Years ago.
So everybody. So, yeah, we don't need too much of calculus. We need to understand what are derivatives that are normals, and we need kind of understanding that sometimes there is partial derivative by x and by y. Mostly that's what we'll need. We have to use the notion of integrals, but nothing that we actually need to calculate any integrals. So we talked about the many applications of texture, like you add with one pass specular to the shape, making shape much more interesting. But I want to meditate a bit on this point, even though we did go over it. I have an image of pixels, and I need to assign every point on this triangle to a point on this image. And hopefully in parallel, and hopefully using everything that OpenGL does to do it. But you do need to understand the algorithm. So what was the rasterization algorithm per triangle did? We went through it a few times. I need the barycentric coordinate of every point in the triangle, which I don't even need to know whether I used OpenGL WebGL, because I can just use the location and all this linear interpolation happens without me taking active steps about it. But for the point P, I need to calculate, and I can definitely ask you, how can I calculate it efficiently? The barycentric coordinates of every pixel, not every point in the triangle. I don't need an answer for all the infinitely many points. I just know that there are certain rows and columns that interest me in this triangle, depending on the pixels of the original image. And now when I have the three numbers, these barycentric coordinate of each point P in the triangle, what do I do? How do I know to which pixel in the image I need to retrieve? Well, ahead of time, I need to say that this point, this vertex of the triangle, I'll assign it to, say, the top of the image. B, I'll assign to the point B prime. C to C somewhere here outside the slide. And now, you told me what is a point A prime, like a vector, like what are the coordinates of the pixels. So for B prime, it will probably be 0, 0, and in the lower left corner of this image. So B prime will be probably 0, 0. A prime will be maybe 0 and 10 in this example. See, and now you have, for every point P, you have different barycentric coordinate. WA, W of B, W of C. All I need to do is to take the ij of A prime, B prime, C prime. That's I did when I glued the triangle to this texture. And which pixel should I look at? What is its ij coordinates in the image? It will be WA times the I, what I assign to A, plus WB, what I assign to B, WC, what I assign to C. Excluding numerical error, could it be that this number is outside the image range? Assuming that I assigned A, B, and C to be in the image. You said no, everybody agrees? Why? No is the correct answer. Why? Because WA, B, and C are convex combinations. They summed up to 1. Don't forget, convex combination. 3 positive numbers that sum up to 1. Mirrors. You have to implement mirrors in homework 2, in homework 4, and you can do it with only, for each mirror, it's just one pass of the one pass of the Z buffer algorithm. Feed the whole scene into the Z buffer, while your color buffer becoming, when you're done, take your color buffer and call it a texture. In OpenGL, I'm not sure about WebGL, you can define it ahead of time as one pass, where you're calling it a texture buffer. I'm not sure about WebGL. WebGL, it will just be the color buffer. And now, what are we doing? I want to generate the mirror of this room over here, what you see in what the eye see in the mirror over here. How do I do it? I place the eye camera at a virtual eye on the different side of the wall that contains the mirror. Mirror is flat here, by the way. On the other side of the mirror, I take the look at direction W minus W, reflected with slight typos. It's not exactly the reflection because the idea, so that's W prime, meaning that I'm, like normally I'm looking at the direction minus W, at the direction to the look at, I'm looking at the minus W prime, that was the reflection by the wall of W, that's the direction that I'm looking at. And then I'm doing one pass, generating in my color buffer everything that the mirror shows. That is, you'll first see closer from the mirror, the red ball is closer than the blue square. Because that's the image that the mirror shows. Again, how do I know what the mirror shows? I think about it as a mirror. No, the mirror is a square. I'll cut in the wall this square. So now it's becoming a window, and I have a camera from outside the room that looks through the window at what happened in this scene. Yeah?
I was thinking, instead of trying to like flip the direction vector from the eye to look at point, couldn't you just apply the formula to flip the eye position to the look at position?
I think that it's the same thing.
Yeah.
If the wall is the x, if the wall is the y-axis, then the flip direction is just take x and multiply it by minus 1, so we're getting minus x, and y stays the same y.
Okay.
That's flipping if the wall is vertical.
Cool, yeah, that's what I
Yeah,
thought.
but it's legit question in the midterm, how would I flip around a general plane, by the way? And that's the answer would be translate the whole thing, by the way, until this general plane becomes the XY plane, and then do the normal flip and translate it, rotate it back. We had it as one of the questions when it was not a plane, it was a line, but now it's legit to ask the same question for a plane. Yeah, in the uncool part would be, I'll give you a specific values of the vector and ask you in real time to compute the numerical value. That's probably would be a no-no. There was other question.
Stupid question probably. If we just take the eye, and why can't we just calculate the rate if we just bounce it off the mirror instead of actually just calculating?
Oh no, okay. If you want, I was spending much more time hearing Sam's course at Utah, which you should do listen to both interactive computer graphics and the intro to computer graphics. There is a link coming up in the slides. In general, if you need high quality images, then you have to do ray tracing. If you need interactive, you must use the buffer. It's clear cut between them. So yeah, ray tracing, yes. I skipped this year homework 3 from last year, where it was multiple mirrors, and then yes, you had to do multiple iteration of array until you finally found something that is a non-mirror, and then finally you know what is the color of this point. Okay. Easier case. Here is a mirror. Here is the center of the mirror. From the center of the mirror, take the normal, and here is the mirror. My camera is somewhere on this line. And then, remember, my GPU wants a clear force-storm. Force-storm, a pyramid, namely, you have the point of view in a perfect square, and you're chopping from this square, shooting it all the way. So you have pyramids with 4 sides, except that you are chopping it at 2 planes, near and far. And your distortion wrap must use it. So why do I say that this is the easier part? Because now I can define the force-term, so it's completely identical to this mirror. That's when the mirror is a square. If the mirror is not a square, I can still get away with this by just scaling in one direction. So it will, if it's rectangle but not a square, I can get away by scaling. But again, the boundary of the mirror of this pyramid coincide with this. Meaning that when I look at the color buffer, I see what the eye, this reflected eye sees, it's only what the mirror shows. There are no other details. But in this image, this is not the case. Like, I cannot make it just a nice force-term. And let's try to understand what's happening here. Here is the eye. Here is the eye. This is a mirror, or the mirror becomes just a window. Meaning, think about it. I look at the wall, everything is opaque except this rectangle, except that the camera is not right here. The camera is not on this line. So here is the mirror. Let's zoom out a bit. And still in this case, the eye is just in the right place, so you can place the part of the force-term below the mirror. The eye here is still on the center, and I can set my view force-term so it's just identified with a mirror. And this is an even easier case. And the image that you'll see, if I just put the eye in the correct place, is here is the image of what I see in the mirror, and outside is the image plane. And if I move the eye a bit lower, that's exactly what I need. And so in this case, again, one pass to generate what the mirror sees, use it as a texture, and basically just copy the whole image, and use it, call it a texture, and now make another pass. When it stopped being a mirror, it just became the normal image, what you saw in the mirror, and now another pass from the location of the real camera. Everybody understand this part before I continue? You're all quiet, which I can understand in many ways. What happened if I'll keep the same force-term? But what do I see right here? I see the mirror in my force-term. So that's the image plane what the color buffer contains on my Z buffer. But this is the only part that I see through the window. Everything outside it are things that's just the other side of the wall. It's not what you want to show. And maybe even I moved the, maybe we are more similar to this case. Here is the camera. Oh, actually, here is the camera, and here is the mirror on the side of the mirror. So what you actually see on the image plane from after this one pass of the Z buffer is the image somewhere here. And if you notice, it's not even a rectangle. the camera is closer to one side of the window, comparing to one side of the window comparing to the other side. So this is larger than this. It's becoming a trapezoid, and if I move it even to the side in the other direction as well, you see even further that it's some strange quadrilateral, but it stopped even being a trapezoid. But you still need to do it. You still have only 2 passes on your Z buffer, so how? It's what I asked you to think of last meeting. You have the whole image plane, the image buffer, color buffer, and why did you not snag it to the boundary of the mirror? Because you're looking at the mirror from the side, so it's, no matter how a frostum looks like you cannot really, it will not be a rectangle. But you still need to implement it in homework 4, so we might as well discuss today what's the main algorithm.
Would you just compute a new frustum for the mirror? Like, does it need to be?
I need to compute the frustum like so, where it contains the mirror. So here is a window, and I need to make sure that the frustum contains a window. So in this case, just part of the window is seen. But I cannot get away from having some dead area on the sides. Maybe not on all sides, but. So I need some extra step in the algorithm. Very easy step. So hopefully everybody is the same page. That's the image that I'm getting. It contains the parts that you see in the mirror. That's what I need to place on the other side as a texture. And there is all the dead areas that I'm not interested in, all the dead bytes, but they are still there. And it's not a rectangle. It could be it will be quadrilateral, hopefully, but not a rectangle.
Put it in the plane of the image somehow?
It's changing the code by very little, but conceptually you're definitely changing something.
Is it also applying the flip to the look-at position?
I need the lookup position, definitely. Let's give you hints. So just remember that usually in modern computer graphics we are not working with quads, we are working with triangles. It's not a solution to the problem, but same way that in homework 3, if you have the texture of a billboard, you use the texture of drawing. Use the texture of the, say, one triangle and then the other triangle. So the hint is in this slide.
what's the problem exactly that we're trying to solve?
If I use what my virtual camera sees, I'll get part of the wall around it. And if I'll adjust the camera parameters, I can maybe have a bit more, a bit less, but I'll still have dead area outside. People that I don't see frequently, you're also welcome to. Yeah, you were about to say?
Oh, totally lost my train of thought. I was going to say do something with texture mapping so that you're mapping those so that you have like a UV coordinate that corresponds to the correct corner of each corner of the quadrilateral, so it's going to turn it into a square when you cycle it.
Once again, I'm moving the point P. Hopefully, didn't play for a while. I put a point. Move the point P, compute the barycentric coordinate, but how do I know what is the ij? It all depends on where did I place A, B, C. So what happened in this case? Here on the side? Yep. Sorry, wrong one. Wrong one as well. Yeah. Pixel 00 of the image is right here. Maybe it's in the dead area. I don't need all the pixels. You're about to suggest a solution? You will half say something.
I thought it was going to be something rotating
It's homography transformation. It's like stretching. It's the image that you see if I'm very close to a flat things, and things over here are larger than things far away. But I'm suggesting maybe I'm over dramatized it by saying that it's a big problem. It's not.
You just map the corners of the image plane to the image of the mirror, or the vice versa like that?
The corner of the mirror are the points in the texture, but not the corner of the texture necessarily. Again, when I decided in the texture what is the point A prime, B prime, and C prime is the texture, nobody told me that these points must be the corner of the texture. It can be some points inside the texture. And then you'll have to take my word that it's only linear in homogeneous coordinates. You don't need to worry about anything else. What you found these 3 points. Where are the corners of the mirrors appear in the image? But how can I do it? How can I find this point in the image? There you're just using what you know from homework to shoot away from that's why I said that if you're definitely using the look, shoot away from the eye to the corner of the mirror. Ask where does this ray hit the image plane. Pick these 3 corners. pick three corners, and that's the triangles that you meet. So you want to get the answer in the UV coordinates. That you think about the image plane as a billboard. Ask where are the corners of the triangles, because they are depending on where the eye is. And in 3D, again, moving the eye change how this image looks like. So the moment that you just found for these 4 ways, where do they hit the image plane, where do they hit the force field, you solve the problem. Okay. So again, one more level of ray tracing, but only for the corners. Yeah.
I'm confused where the problem's coming from, because wouldn't you be interpolating the coordinates of the weird shaped mirror? So I'm still not sure I understand what you would see if we didn't do this. Does that make sense?
If I take the whole, well, that's what I have in my image buffer. There is the window itself. My camera here is just too wide.
This is the new eye position that's been
yes,
reflected?
Yes, that's a new eye position.
Okay.
I put it too far, or I gave it a too wide angle.
Too wide a field of view.
Yeah, I'm on the other side of the wall.
Okay.
And see, my mirror is in the center, just as what I call the easy part, but my force is too wide. Okay. So if I use this whole texture to place it on the wall and then do the pass from the real camera, you'll see the other piece of the wall surrounding the mirror.
I see.
And but
so
you're saying that this problem, why did I make it
view.
complicated? I could have adjust the camera parameter and make it snag. And then I don't have pieces of the wall. If I make the image, the camera parameter that just snags, then I don't have empty part. But in general, I cannot really do it.
I see.
So there are some stupid pixels here that are not part of, from this wall, the camera is right here, the camera is where our mirror sits. We don't see, but that's a real mirror, you don't see the pixel that belongs to the, what we teleport Amir to the other side of this wall, and he's watching from the other side via this mirror. But what he sees is a piece of the other side of the wall. And we don't need them in the mirror itself, because the rest of the mirror is a wall from our side, it's a whiteboard. Okay, image mapping for cylinder, quite easy. Spheres are much harder. Just to give you, and it's not a big deal about cylinder, we don't need them right now, it's a bit promo to modeling and shape representation, but here I have an image, let's say that the image is, well, pixel 1, 0, 1, 1, 1, 2, dot, 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 all the way to 1, 9, same all the way, a few rows, and I want to map it. That was exactly why. I have a poster. I have the label, and I wrap it around the cylinder. Do this process. What should be my mapping? How do I represent a point on the cylinder, assuming that the cylinder has a radius of r? Then a point on the cylinder would be represented by cosine j, sinus j. Why? What are the formula cosine j, sinus j in general? What is it?
Point on a unit circle.
This is just a unit circle. Right? Meaning that each point along the cylinder I can represent as a point on some circle around it, and how high it is on the cylinder itself. What does it fit to when I do this wrapping, then I take the label and wrap it. Again, think about, I don't want to destroy it completely, think that I cut this piece, kind of unwrap it, and then wrap it again. What happens? Points on the x, y, pixel ij is mapped to pixel on the cylinder, for which x is cosine, y is sine, j is at which row m, and the elevation is just fits into one row of the cylinder. Make sense? Play with this. The lowermost row of the image fits to the lowermost row of the cylinder. We're just walking around the cylinder, starting at 1, 2, 3. As you're rotating around the cylinder, let's get a bit more height. As I'm rotating around the cylinder, it's like wrapping something around it. Okay, and that relates a bit to surface of revolution that we'll discuss later. We're getting to the second part of the homework, which is shadows. Shadows, but that we'll have to wait maybe for a bit of the Monday with a review, or all the way to. So to generate shadow, big deal. We are doing one pass from where the light is, except that we don't care what the image that the camera generated. We care just about the distances from the images to each of the object. How do we know what is distances? That's exactly what the depth buffer tells you. And now I'm generating one pass from the depth buffer and one pass from where the real camera, one pass where my camera is in the source of light, works for 1 point spot source of light, generate the depth out of it, throw away the image that you created from the light, and then do one pass from the real camera, where for every point that you see, you indicate if it's in the right distance from the light. If this point, the distance from the light of this point, the light, think about this point, it says, no, the distance to my nearest object is smaller than the distance to this point. Conclusion, this point is in the dark because there is something closer to the light along this